grown to include over 20 members, mostly from mechatronics systems engineering, but also including students from other programs and faculties. We couldn't have imagined all that we could have accomplished since the team was founded and what the team has become. We are proud to provide an opportunity for students to gain hands-on experience outside of the classroom, applying their engineering knowledge to real-world scenarios. Our team consists of members from all years of study, with the more senior members mentoring the junior members, who not only represent the future leaders of Team Guardian, but also the future leaders in their careers. The immense value that is gained through an opportunity like Team Guardian is unparalleled in the university experience. Since the team was founded, we have participated every year in the Unmanned Systems Canada competition. This competition uses real-world scenarios such as wildlife surveying, agricultural surveying, and search and rescue applications to base its objectives on. It has grown to include over 15 teams from some of Canada's top universities. Since we participated, we have achieved a second place finish twice in our history, most recently just last year in 2016. Our team was up in northern Quebec just earlier this year in April to represent SFU once again. Now, in the past, we have been flying exclusively with fixed-wing airframe, much like the one you see behind us. But this year, we wanted to try something new. We were going to fly the fixed-wing airframe along with a rotary-wing airframe, or what's more commonly known as a drone. This will allow us to use a fixed-wing airframe for high-altitude surveying, taking high-resolution pictures, and from the data we collect, we can send out the rotary wing to perform more mission-oriented tasks, such as obtaining higher quality images, or even performing object delivery or retrieval. Unfortunately, at competition this year, a combination of major objective changes, hardware changes, and poor weather caused us not to place, but it left us more motivated to create a robust unmanned aerial vehicle solution. Our plans to attend the International AUVSI student competition were put to a halt, unfortunately due to some funding issues, but instead of letting the development time we spent preparing for this go to waste, we wanted to prepare the same scenario that they gave us. We want to present that for you here today. So we'll be simulating the exact same scenario, which I'll go over in a moment, with our hexacopter, which is already out in the field. We've got 9 of our members representing our team today. So with me we have Vadim, who is our safety pilot, and he has also worked extensively to develop our target analysis and geolocation software, or TAG software, which will be used today. Richard is our autopilot operator, and he will be overseeing the automated flight, and it will be using the customized software that he's used to generate the flight plan automatically. We've got Sid, who is our vision system imaging lead, and he'll be operating the TAG software, which he's also helped develop, and he's also been involved with all camera controls, from everything from obtaining the camera to making sure we can control it from the ground when it's in the air. We've got Alan, who is, he also serves as our fixed wing pilot. He's also worked this year to develop the software algorithms, which will be used in our custom antenna tracker, which you'll see operating during our flight. Nikita is our mechanical lead for the team, and this year he's also become our 3D printing expert. You'll see many orange and blue parts that we're using both on the hexacopter and the antenna tracker, and a lot of these he's designed himself. And the antenna tracker itself, he designed and fabricated that all on his own. So we're excited to see it working today. We've got Andrew, who is part of our mechanical team and has also been working today to set up the mission simulation that we're going to run for you shortly. Andre is has worked hard to develop software for both our vision system and autopilot teams, and he's worked to improve the accuracy of our geolocation so that we can get accurate GPS coordinates of every pixel from the images we take in the air. And finally, we've got Cyril, who is our most junior member, but even though he's the newest on the team, he's already had an opportunity to dig his hands into some software work for both our vision system and autopilot teams. The scenario that we're going to be performing today is to assist a search and rescue crew in locating a lost hiker. We're also going to be delivering emergency supplies, which in this case will be a water bottle. The hiker has also placed a series of clues throughout the field, which are represented by alphanumerics on targets of different shapes and colors. We are given the last known position of this hiker, but we don't know its current position, so we'll have to do some searching around to find its current location. We are given the mission parameters on a server, so we must first download all these parameters to our ground control station. Our software will then interpret this data and will automatically generate a flight plan that will execute. Before we can start our search for the hiker, we have to fly a series of waypoints. And you can be watching on our display here, the waypoints are represented by the blue points. This is to simulate a path that we must navigate before we can enter the search area. The first waypoint will also serve as a point at which we drop our water bottle, and we'll compare the accuracy with which we can get the water bottle on the target. You'll also see on the display a red object, and this is to simulate an object that we must avoid in flight, which could be a building or a tree. The software will have to automatically fly through these waypoints, avoid objects, and perform its search from these details given. The white area is our designated search pattern. So after we fly the waypoints, we'll be searching through that area where the hiker has placed his clues. The pictures are sent in real time back to our ground control stations where they can be processed, and we can identify the targets and send them back to the server before the UAV even lands. And finally, the UAV will go to the last known position of the hiker and begin a search to find where it currently is. For this scenario, we are assuming that the hiker is within a given radius, just because of the limited space we have available to us. Once we start flying, if you want to take a look at the display, you'll also see a green dot, which represents the position of our UAV during the flight, as it sends its telemetry first back to the ground control station, and then is relayed over to the server for our viewing. Once we land, we'll score our mission based on a variety of factors, including how accurate we can hit the series of waypoints, how accurately we can drop the water bottle on our target, and the characteristic and location of the clues the hiker gave, and the location of the hiker itself. We'll have Vadim give a summary of our mission performance after the flight, but first we're going to run the mission demonstration now. So we've got a radio with us, so we'll be able to listen to some of the communication that happens between our ground control and our pilot. And I just ask that, especially for takeoff and landing, that you remain under the tent so that we can respect our the regulations set out by Transport Canada for us. But as the hexacoupler moves out, you can feel free to use the space a little bit more freely, and you can always feel free to watch. So I'll let you guys set up.
One more point, if I can ask. If you have any questions during the flight demonstration, please remember them, and you will be able to ask them in the Q&A session following the mission plan. This is because Chris will be explaining what we do throughout the mission, and so answering any questions would interrupt that process.